the sequence of chapter 8 very closely follows the sequence of chapter 7. And so in 7.4 and 7.5, we talked about the confidence interval for proportions. So we're going to do the exact same thing in chapter 8. This is the standard definition of a proportion. So it's the number of successes divided by the number of trials. And that will give you this value called p hat. Okay. In the previous sections, this was the mean, right? The mean was the value that we were looking for, and that was the value that we were comparing, the important statistic in the sample set. In 8.4, it's no longer the mean, it's the proportion. That's what we're looking for. And so this is how you calculate the proportion. You then are going to take that proportion and we're going to calculate a z-score. And so if you have a large population, you do a z-score. This is the difference, and this is again reflecting back to what we did before. When we did the z-score for the mean, you took the sample mean, so this was the sample mean, and you subtracted the population mean. And then you took the standard deviation from the population and divided by the square root of the number of items. And that would give you the z-score when you're talking about means, okay? We don't have means. We don't have these values. Instead, we have proportions. So we need a different equation to calculate our z-score. And here is the equation to calculate the z-score for a proportion. So this is the proportion of the sample. So that is this guy. And this is the proportion of the population. And so you're going to find the difference in the p proportions of the sample and of the population. Then you're going to divide by the square root of p times q over n, where p is again, the sample proportion, the probability of success, and q is the probability of failure, both for the sample, divided by how many items are in your sample. And that's how you get the z-score. Again, this will be done in a spreadsheet through the algorithm for you, but it's good to know that this is the equation to calculate the z-score with proportions. So now we're back into the routine of, well, how do we do a hypothesis test? So first you identify your variable and the proportion of that variable. The null hypothesis is that the sample proportion and the population proportion are the same. So that's our null hypothesis, that there's no difference between the sample and the population. They're identical. And then our alternative hypothesis is that either the sample is less than the population, greater than population, or not equal to the population. And again, this gets back into, we're going to have a normal distribution, and you're either going to shade below for the less than, above for the greater than, or both for not equals to. Okay, so you're going to find that area either below, above, or both, and then you're going to compare that to some certain threshold, usually 5%. Okay, in order to proceed on this, there's a couple stipulations that we have to make, because a lot of times proportions are binomial distributions, either yes or no. Either you met the condition or you didn't meet the condition. That's what proportions usually are. So in order to say that a proportion can act like a normal distribution, in order for this binomial distribution to behave like a normal distribution, we have to have a couple things happen. Number one, n times p has to be greater than or equal to 5. So the number of items times the probability of success has to be greater than 5. And the number of items times the probability of failure has to be greater than 5. Now, of course, these conditions are going to be met, but it's something that we have to allude to just in case you wonder, can I proceed with this? This is why we can continue and use a normal distribution on this, even though it's a binomial distribution. And so if these two conditions are met, then the binomial distribution will approximate a normal curve, and we're good to go. Okay, and these conditions more times than not will be met. So what do we need? What data do we need? We need the proportion. We're going to take that, we're going to calculate the z-score, and once we have the z-score, we're going to calculate a p-value, and then we're going to either reject or fail to reject the null hypothesis and then have an interpretation. So here's an example. This was, in these examples we used previously, but now instead of finding a confidence interval, we're now finding a hypothesis. We're now going to make a hypothesis and see if our hypothesis can be rejected or failed to reject. So in this case, this example problem, there was a concern raised that the proportion of Aboriginal prisoner deaths was higher than the proportion of non-Aboriginal prisoner deaths. And so this number here, this is our population. That's our population proportion. That is P sub 0, okay? And the claim is that there's no difference, right? That's the null hypothesis, that the sample and the population are completely the same. Instead, we need to come up with a sample proportion. So here's our sample, and we're going to divide these two numbers to get the proportion. You'll see that in a little bit. And we're going to test this at the 5% significance level. So here we go. What are our variables? Aboriginal prisoners who died, the number of them, divided by the total number of Aboriginal prisoners. We use that to calculate an alternative hypothesis. So again, this is our null. This is the population proportion. And we believe our alternative hypothesis is that actually it's higher, that the Aboriginal p-value is higher than the population p-value. And we're going to test it at the 5% level. So first of all, this is bimodal, so there's only two choices. To make sure that we can use a normal distribution on this, we have to make sure that n times p is greater than 5, and it is, and n times q is greater than 5, and it is. So cool. That means that even though it's binomial, we can use the normal distribution mathematics in order to solve it. So here's our number of Aboriginal prisoners who died out of the total number of prisoners. This is our p hat value. So this is our proportion. And now we take that proportion and we put it in to find a z-score. So this is p hat. This is p0. This is the population proportion. And then we put in p here and q here and n here. And this is the number that we get. So what that means is that if you were to take the entire population and graph it on a normal distribution, that this proportion, the proportion, this z-test statistic would be 1, 2, it'd be right here. It'd be 1.8979 standard deviations away from the original proportion, the population proportion. And so this is the line, this is our target, and we believe it's greater than this target. So we want to find the area above this target because we believe it's greater than. And so 2 standard deviations is usually considered an outlier. So this should have, some area underneath it. It's not going to be a really small number. And so if we graph this out, it actually looks like this. And if we calculate the area under that using either Google Sheets or Desmos, we get this area is equal to 2.9.0298854, or about 2.9%. So because the 2.9% is less than our threshold of 5%, that's good. That means we get to reject the null hypothesis and that we can actually say there is enough evidence to show that the proportion of deaths of Aboriginal prisoners is more than for non-Aboriginal prisoners. Okay, so that's the entire process. I think we got one more example. This was, infants being fed formula. High-income countries versus low-income countries. So you would say that the proportion of infants that are fed formula in low-income countries is equal to the proportion of high-income countries. This would be our null hypothesis, okay? That's this guy. And that happens to be, for the high income, 0.22. The researcher believes that low-income countries have a higher rate of infants fed formula. So again, this means above. And so when you see this higher rate, you're thinking, okay, we're going to do something like this. We got to find this magic number, and we're going to find the area above that curve. Okay, so a couple things should be triggered in your head when you see this vocabulary. And so this is the population p-value, and our alternative hypothesis is that it's greater than, that it actually should be greater than that. And we're going to test at the 5% threshold. So we want to make sure that we can approximate this using normal distribution mathematics. So n times p has to be greater than 5, check, it is. N times q has to be greater than 5, check, it is, good. And so here we go. The sample, actually this is the population proportion. I have to make an adjustment to that. So the population proportion is 0.22. Our sample is this, which gives us a sample proportion of 0.25. So is that significant at the 5% threshold? So we're going to take the sample p-value, and we're going to take the population p-value, and then we're going to take those and plug them into here, chink, 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 and we get a z-score of this. And again, this 1.6194 means that our sample, if this is the population right here at 0, our sample is right here. So this is our sample p-value, p-hat, and it is 1.62 standard deviations above the population proportion. That's what that z-score means. And we've done this for a long time. We've been playing with these z-scores for a couple chapters. So if you take a look at that number, it turns out that that p-value, this area, is 5.2, which is greater than our significance level. So that's bad. That means we don't get to reject the null. We fail to reject the null hypothesis. So we have to fail to reject the null hypothesis. It remains king of the mountain, and our alternative hypothesis is canceled. So the interpretation is there's not enough evidence to show that low-income countries have a higher rate of infants fed formula at the 5% level. Okay, so hopefully some of this feels familiar to you. Like it's kind of like we're mashing a lot of things together. We're now dealing with proportions, so you got P's and Q's, but you're also dealing with hypothesis testing and finding the area under the curve and comparing that to a threshold and seeing if that p-value is above the threshold or below the threshold, and then either accepting or rejecting the null hypothesis. Okay, so here's the 8.4 homework, and the first couple problems on 8.4 homework just ask you to find the z-score. And this is the 8.4 tech tool. So here you can see our null hypothesis is 0.48. So I'm going to type in 48 divided by 100. So that gives me my population p-value of 0.48. Okay, great. And then we go out and we collect the sample of 131 subjects with 65 successes. So 65 is the number of successes. 131 is the number of subjects. And this is our p-value. So we just divide those two numbers, that's p. Our q value is the complement of p. So 1 minus p gives us the q value. We take that and we throw it into that formula for the calculation of the z-score. So we subtract the two proportions and then divide by the square root of blah, 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 blah. And here's the z-score. And then we find the area below and the area above. And so when you take a look at this guy, all we're asked is the z-score. So I should be able to copy the z-score right here, copy it, and I should be able to paste it here. And we got it right. I probably should have rounded it to 2 decimal places because sometimes, as you know, if you don't do the rounding, it will mark it wrong. But in this case, we got away with 1, so I guess that's all right. Past study indicates that the percentage of smokers was estimated to be about 34%. So this is our population. So we are going to say that our null hypothesis, and notice what they have here. They have P's for proportions and mu's for means. We're not dealing with a mean. We're dealing with proportions. And so you always want to select the value of P here. So we're going to say P is equal to 0.34. That would be our null hypothesis, okay? Given the new smoking, blah, 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 you now believe that the percentage of smokers has been reduced. So our null hypothesis is going to be that P is less than 0.34. So here's the population, and then this is our alternative hypothesis, less than, because it's been reduced. Because it's less than, that means this is going to be left-tailed, okay? So identify the significance level. I think we're coming in at 0.5% for the significance level right here. So we type that in. Calculate your test statistic. So that's going to be our z-score. So we put in our sheet, what do we got? 34, so that's 34 over 100. And then we randomly surveyed 2,139 people. And out of those, 674 were smokers. And here is our p-value. This is our value for Q. And this is our test statistic. So I'm going to copy this guy. And we'll paste it right here. Boop. Okay. So negative 2.4, blah, 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 blah. Then we calculate the p-value, the area under that curve. And here it is. Here's the area below the one-tailed. So we're going to copy this, and we're going to paste it here. Now, this is why it's important to understand your problem, because if this was a not equals to, you would have to take that area under one tail and multiply it by 2, right? Because you'd have above one tail and below the other. And so looking at this value is way below 5%, so that's good. That means we get to reject the null hypothesis since the p-value is less than the significance level. So we'll select that one. That looks correct. And then there is sufficient evidence to warrant rejection of the claim that the percentage of smokers is less than. No. There is not sufficient evidence to warrant rejection. The sample data supports the claim that the percentage of smokers is less than that. There's not sufficient evidence. We're going to go with this one and see what happens. See if my numbers, I wonder if they want me to round. Round your answer to 4 decimal places. 1, 2, 3, 4. I bet you they got me on that. These other ones look pretty good. Yeah, that's what it was. So in D, you can see I can put more than 2 decimal places in there, but in letter E, you got to round it to 4 decimal places, otherwise it'll mark you wrong. So always round when they ask you to round. Make sure that you're rounding. Sometimes you can get away with it, but other times you can't. All right, so that's 8.4.